Let us look at comparison test 1. Now we have seen for a geometric series, it was easy to apply the Cauchy criterion since tail sums are explicit or easy to estimate. For most other series, no usable closed form expression for tail sums, no simple bounds, and no uniform control in the parameter p. Now, just to give you a taste of that, if you remember in the previous geometric series discussion, we had to evaluate m for this. That is, we had to figure out for what value of m will this inequality hold. And in that session, I actually did it manually. M plus 1 equal to 1, m plus 1 equal to 2, and so on. But we could have done it in a much more rigorous way, in the sense, instead of hit and trial basis, we could have written 1 by 3 to the power of m plus 1 as 3 to the power of minus m plus 1 less than 1 by 150 and taken the reciprocal. So inequality changes. So 3 to the power of m plus 1 is greater than 150. Now taking the log on both sides, we get m plus 1 times natural log of 3 is greater than natural log of 150. So m is greater than natural log of 150 divided by 3 minus 1. So we would have got m is greater than 4.56 minus 1, which is m is greater than 3.56. Since we are interested in integers, that is m is greater than or equal to 4. So this is much more systematic. Instead of trying out one by one all the values of m. Now to simplify it further, we have other methods. Now remember, we have other tests which guarantee Cauchy criterion. And the first one of those that we are going to look at is the comparison test 1. Now let's look at it from a convergence point of view. Given two series, u sub n and v sub n, where u sub n, all the terms of the u series is greater than or equal to 0, and all the terms of the series v sub n is greater than or equal to 0. Now, here we know the convergence of v sub n. We have to figure out the convergence of u sub n. So, the series u sub n is convergent if u sub n is less than or equal to k times v sub n for all n greater than or equal to m in natural numbers and k is greater than 0. So let s sub n equal to v1 plus v2 plus v3 and so on up to v sub n be the nth partial sum of the series v sub n. Since the series v sub n is convergent, let limit as n goes to infinity of s sub n be equal to L. Let t sub n equal to u1 plus u2 plus u3 up to un be the nth partial sum of u series. Now, t sub n is less than or equal to, because we already have that u sub n is less than or equal to k times. So let's say t sub n is less than or equal to k times v sub 1 plus k times v sub 2 plus k times v sub 3 plus up to k times v sub n. So t sub n is less than or equal to k times, k is common to all of them, k times v1 plus v2 v plus v3 plus v4 plus dot 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 v sub n is nothing but s sub n. So we have t sub n is less than or equal to k times s sub n, and u sub n is greater than or equal to 0 for all n in natural numbers, which implies the sequence of partial sums t sub n is monotonically increasing. And since t sub n is less than or equal to k times s sub n, and the sequence of partial sums S sub n is bounded implies T sub n is also bounded above. The sequence of partial sums T sub n is convergent and therefore the series U sub n is convergent. Okay, later on we will look at an example for this, but now let's look at it from divergence point of view. Now, given two series U sub n and V sub n, where U sub n is greater than or equal to 0 and V sub n is greater than or equal to 0. These are the series and these are the terms of those series for all n in natural numbers. Now, assuming the series V sub n is divergent and S sub n, the nth partial sum, goes to infinity. So S sub n is equal to the nth partial sum of V sub n. Further assume that there exists k greater than 0 and m in n such that U sub n is greater than or equal to k times V sub n for all n greater than or equal to m. Let T sub n be equal to U1 plus U2 plus U3 up to Un be the nth partial sum of the series U sub n. Since U sub n is greater than or equal to 0 for all n, the sequence of partial sums T sub n is increasing. Similarly, since V sub n is greater than or equal to 0, the sequence of partial sums S sub n is increasing. For all n greater than or equal to m, we have T sub n is greater than or equal to k times S sub n. Since S sub n goes to infinity, implies k times S sub n goes to infinity. But k times S sub n is nothing but T sub n. So hence T sub n goes to infinity. Therefore, the sequence of partial sums T sub n diverges and consequently the series U sub n diverges. Now let's look at an example for convergence. Now we have this given series. Now we have to compare it to another series. So let's figure out which series should we take. Now we know for n greater than or equal to 1, n square plus 1 is greater than or equal to n square because here there is plus 1. That means if we take the reciprocal, the inequality reverses. So 1 by n square plus 1 is less than or equal to 1 by n square. So we have found the series that we need to compare this series with. But we know that the series 1 by n square converges. Since 1 by n square plus 1 is between 0 and 1 by n square, the given series converges. So without getting into any problems, we have figured out that this series converges based on another series which we know converges. Okay, now let's look at an example with respect to divergence. Now let's look at this series 1 by root n. For all n greater than or equal to 1, we know that root n is less than or equal to n, which implies 1 by root n is greater than or equal to 1 by n. But 1 by n diverges. The series 1 by n diverges. Therefore, the series 1 by root n also diverges. So here, remember, the tricky part is to figure out which series do we compare the given series with. Once we have that, it becomes very easy to figure out whether the given series is convergent or divergent. So that was comparison test 1. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.